Hi, I'm Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing work and energy. If you recall back to your general physics class, work was defined as force times the displacement over which a force acted. So expressed in integral form, we have work going from some initial position to some final position of force dot dl. Now we're talking about electrostatics here, and the electrostatic force is just Q times E. But we're considering the amount of work that you have to do, the force that you have to exert against the field. So therefore, instead of QE, we're going to write this as minus QE. And if we make use, again, of the relation between the electric field and the potential, we wind up with an expression of an integral from some initial to some final position of Q, the charge, times the gradient of the potential dotted into the line element. And using the fundamental theorem of gradients, this just becomes Q times the change in potential. The potential evaluated at the final position minus the potential evaluated at the initial position. Now, oftentimes we're interested in the amount of change in potential between an object that is way out in infinity and then when it's brought in somewhere closer. So if I change this around, we have Q V as a function of position minus Q potential evaluated at infinity, which we take as our reference point for point charges. So the second term vanishes. And I'm left with the work done is equal to Q times the potential. We can state this another way in terms of the potential difference in terms of the work. And that's equal to the work per unit charge. I next want to figure out what energy is associated with an assemblage of charges. So how are we going to do that? Well, we know what the potential is due to a point charge. It's just going to have the value QI, and we'll just call this charge I for now, over 4 pi epsilon naught divided by the magnitude of the separation vector, where R is a field point, observation point, if you will, minus the location of the charge itself. Okay. So let's say that we have nothing to begin with, and we're going to bring in one charge from infinity to where we are right now. Well, if there's nothing here, we don't have to do work against anything. So it costs us nothing to bring in the first charge. So in other words, we have nothing around us, no charges, no fields. The amount of energy it takes to, or work we have to do to bring in that charge from infinity to where we are right now costs nothing. So to bring in the first charge, first charge from infinity costs us nothing, and therefore the work that has to be done is also 0. How about the second charge? Now you do have a point charge. point charge is going to give rise to potential. So I'm going to have to do work to bring that second charge in. And therefore, is going to be equal to the magnitude of the charge, or rather the charge Q2, times the potential. Due to charge 1. That's located at position R1. And we're bringing our second charge into position R2, and that's the amount of work that we have to do. To bring in the third charge now, we have to take into account not only the field due to the first charge, but also the field due to the second charge. So the work that we need to do in bringing the third charge looks like this. And that's equal to Q3, Q1 over 4 pi epsilon naught, magnitude and separation vector between charges R1 and R3. And also, the contribution to the work term, Q3 times the potential due to the second charge that Q3 experiences. So that's Q2 over 4 pi epsilon naught, magnitude of the separation vector R2 minus R3. So if I continue on with this procedure and keep assembling charges in from infinity, just have to sum up all these terms. Remember, there's no work done to bring the first charge. The second charge is just a single term. Third charge, now we've got 2 terms. We add all those contributions up. It's going to look like this. Double summation, I equals 1 to n where it's the number of charges, and j equals 1 to n where it's the number of charges again, with the restriction that the index, the dummy index j, has to be larger than the dummy index I. And that's qi, qj over 4 pi epsilon naught, magnitude of the separation vector between ri and rj. Writing this a little bit more compactly, or a little bit neater form, I should say, I can do this as 1/2 summation I equals 1 to n summation j equals 1 to n with the restriction that j is not equal to I. Qi, qj over 4 pi epsilon naught, magnitude of the separation vector again. Pull the qi out from behind this j equal 1 summation. Now I'm just going to qj over 4 pi epsilon naught over magnitude of the separation vector. If I recognize that this second summation is actually the potential that qi is experiencing, I can rewrite this as 1/2 summation I equals 1 to A of QI VI. And that is the amount of work done that it takes to assemble charges. It's also equal to the change in energy of the system. Also useful to express this in integral form in case that we don't have discrete charge, that we can describe systems as a continuum of charge. And you know the rule for converting from system discrete charges to a continuum. Just change the summation sign to an integral sign. And we change our charge Q to charge density rho. And that is how you calculate the work done to assemble a system of charges that can be characterized by some potential rho, or sorry, by some charge density rho, and the potential. Okay. Sometimes too, it might be useful to express this in a different form. We've calculated the work done in terms of the charges, but it would be nice if we could come up with an expression expressing that in terms of the electric field. So I'm going to do that. We'll just recall what divergence of E is. It's just equal to rho over epsilon naught. I'm also going to make use of the fact that the electric field is equal to minus the gradient of the potential. I'm going to substitute this first expression into here. And I'll pull the epsilon naught out front. Now we're calculating the divergence of E times the potential integrated over some volume. And so what volume are we talking about here? Well, it's where this term is not vanishing. It doesn't really matter in the sense that when you're outside a certain region, rho is going to vanish. So basically we're just integrating this over where rho is equal to non-zero. Okay. How do I proceed? Well, this is where you want to make use of some of those vector identities that we discussed earlier. Recall that if you have the divergence of the product of a scalar and a vector, that was the same thing as the sum of the vector dotted into the gradient of the scalar plus scalar times the divergence of the vector. So in this case, we're just talking about some arbitrary function f, scalar function f, and some arbitrary vector a. So if I compare this with this expression, this term down here is clearly this one. So I can write this as the difference between this term and this term. So that's equal to epsilon naught over 2. The integral of the divergence of the product of the potential and the electric field minus epsilon naught over 2 the electric field dotted into the gradient of the potential. Step is what? Well, let's replace that divergence integrated over volume by a surface integral. So call from the divergence theorem. I'll just write it up here. So we have for any vector A integrated over some surface, closed surface, that's equal to the divergence of that same vector and integrated over that volume that is enclosed by that surface. So therefore I can replace this first expression with potential times electric field dotted into normal and integrated over the surface. Second term, I'm going to make the substitution that the gradient of the potential is equal to minus the electric field. Okay, I mentioned before about what volume or what region space are we integrating over. I said that here, charge density was non-zero in certain region, 0 outside. So if we just integrated up where rho was non-zero, say it was all squared. But why not extend this integral to encompass all space? Why not, after all? Because rho is going to vanish out there anyway. So if I say that, okay, I'm going to expand this from just a small region space to all to infinitely large radius, or very, very large radius. What happens to this interval here? Well, how do these quantities go as a function of r? Your potential goes as a function of 1 over r. The electric field goes as a function of 1 over r squared. But we're integrating over the surface area, so that's going to give us an r squared in the numerator. But we're still going to be left with a 1 over r. So we're integrating the surface of this integral that goes as 1 over r, and we're evaluating it out of infinity. So therefore, this term goes to 0, and our expression for work is equal to epsilon naught over 2 times the volume integral of the electric field squared. And that's your second expression for calculating the energy. By the way, a lot of authors use the character U to designate the energy or potential energy of a system. I'm sticking with W because that is consistent with the notation of Griffiths, which is, if it's not the most popular electromagnetism textbook, it is certainly up there. So I'm going to use his notation, and he calls that W. So we have two expressions for calculating the energy or change in energy of the system, if you will, and one in terms of the electric field, and the other given in terms of the charge. And that's an important thing, because after all, if field theory is to be a valid representation of physical reality, we have to be able to describe work and energy in terms of that field. Things like work, energy, and force. We've come up with two expressions here, and I'm going to evaluate this for, you guessed it again, a uniformly charged conducting sphere. So let's calculate the work associated with that kind of a system. Write it. My expressions for work over here again. So this is 1/2 volume integral of the charge density times the potential, and also we have epsilon naught over 2 times E squared volume integral of E squared. And this is, you know, down here that's over all space. And up here, this is or a charge density is not equal to 0. So, the system that we've investigated many, many times, calculating the electric field a variety of ways, calculating the potential a variety of ways, and now calculating the work several ways. And just to remind you, what's the electric field? It vanishes for r less than radius. Electric fields vanish inside conductors, so that is what we have here. Now, for r greater than the radius, we have q over 4 pi epsilon naught r squared in the radial direction for r greater than r. And sigma is just equal to q over 4 pi r squared. Now for our charge density, right here is equal to q over 4 pi capital R cubed over 3, and potential is equal to q over 4 pi epsilon naught big R inside and on the surface. Surface is an equal potential. And outside potential is equal to q over 4 pi epsilon naught little r. And notice your potential is continuous across the boundary. Your electric field, however, has a discontinuity in it. I'm going to calculate the work first using this expression. I can pull rho out of the integral because that's constant. Well, actually, since our charge is simply confined to the surface, we can rewrite this as this is sigma v dA. And let me pull sigma out. So that's sigma over 2 and surface integral of the potential. Getting r squared term because of the integrating over a surface element. Remember, surface element is equal to big R squared sine theta d theta d phi. And we know the potential is just equal to q over 4 pi epsilon naught big R there. And these two surface intervals are just going to give us 4 pi. That 4 pi is going to cancel with that one. And we'll be left with sigma q big R over 2 epsilon naught, but it's more useful to write sigma out in terms of q. And we're going to be left with q squared over 8 pi epsilon naught big R. Let's calculate the work done using the electric field expression. Now here we're going to have to break our integral into two parts because the electric field is 0 inside the sphere and it's non-zero outside. integrating over something that's over to integrate on 0, so that first term's going to vanish. And I'm just going to leave one integral sign up there to save myself a little bit of work. Okay, the second one is going to go from big R to infinity. And we've got q over 4 pi epsilon naught r squared, quantity squared, little r squared dr times sine theta d theta d phi. And I should really have a couple more integral signs there. Okay, the first term just vanishes. We don't get anything from the inside. The second term, we pull all that constant values out front. And the integral over the thetas and phis are just going to give us 4 pi. And r squared cancels with one of the r squareds down here. And when I do the math, this is just going to give me 1 over big R. So I'm making all those cancellations and whatnot. I will wind up, once again, very thankfully, with the same answer, q squared over 8 pi epsilon naught big R. That seems convenient, right, to be able to use either of these expressions. You can calculate the work done or associated with a assemblage of uniformly shaped charge distribution, or where it's characterized by a constant rho. And the answer for that I'll just give you, in case you want to go ahead and work that out yourself. And the answer there for uniformly charged sphere is 3q squared over 20 pi epsilon naught big R. So that's good. Good exercise to go ahead and do the math on that. Let's look at the work associated, the energy associated with point charge. Well, if it's a point charge, I don't have to integrate anything. I can just write down the answer. It's just going to be Q times whatever potential that happens to be in that particular region of space. So that's that part. What about work done with using the second expression, using the electric field? This integral looks pretty much like that one, except that, remember, we were just integrating exterior to the region of the sphere, not inside the sphere itself, because the electric field was 0 there. Okay, so I'm going to the same q squared over 4 pi epsilon r squared, sine theta d theta d phi. Again, those are going to give me 4 pi. But look at what happens here. I'm evaluating the integral over all space. 0 to infinity of dr over r squared. And look at what happens here. We wind up with an infinity. I mentioned it before, infinities, generally speaking, are not a good thing. And it's not a good thing here either. So where's the rub? How can one expression work, right? We went through all this formulas and developed it. We seem to be very careful about going from step to step. And yet, when I try to apply this expression to calculating calculating the energy associated with the point charge, I wind up with an infinity. So how in the world did this happen here? It's obviously a little bit of a problem. And the answer is, these are a little bit different. Despite the fact that I said when we went from the summation expression over here, I said, well, going from here to here, going from a series of discrete charges over to a continuum of charge, basically just a little bit of a difference. In this expression, this VI excludes the potential associated with the charge at I, okay? I go from here to here, this is a potential due to every charge. And it's perhaps a little bit useful to go backwards from this expression here, okay? So, when I write E squared is equal to, or rather E, is equal to a superposition of the electric field due to each of the charges, okay? When I do E dot E, basically, which is what I have when I calculate E squared, dotting this E with this E. Got one term where I'm calculating EI squared. And another term where I'm just taking EI dot EJ. So these pertain to two different particles. This pertains to the same particle. This first term actually doesn't depend on the position of the charge itself. But it's clearly some kind of energy. It's infinite. It goes infinite when we try to calculate the energy associated with it. So, as a matter of fact, it doesn't depend on the position of the charge. What it actually is the energy associated with making the charge. And we don't have any control over that. That's not what we're studying here. We're not studying how to make charges up or how to pull them apart either. The only thing we're interested in calculating is how do we reposition, how do we pull charges in from infinity, what's the change in energy of the system when I do that. This term has to do with the energy associated with making the charges themselves. It's called self-energy. And we do not trouble ourselves with it. If you're looking at this saying, gee, it seems like we're playing a little bit fast and loose, cutting out certain parts, that just because they're infinite, we can just get rid of them and not worry about it. It is, yes, a little bit of a problem here. I will say in electromagnetism, it's unfortunately, I'm not really sure of how to handle this other than to just recognize that it's the energy associated with making the particles themselves. But the fact of the matter is, we're not worried with that. As I said before, we're just worried with reassembling charges, pulling them in, calculating the change in energy in the system due to moving charges around, not actually making them. So this term is actually a safe bet when you're calculating the energy associated with just doing the work with pulling charges in. This is actually a more complete expression because it contains not only that energy associated with pulling the charges in, it's the energy associated with creating the charges as well. So in the case if you're talking about point charges, you cannot use this expression when you're dealing with problems like the one I just did. Either of these expressions is equally valid. Now, you might notice another little difference as well. This actually can be negative, whereas this expression is always going to be positive. And again, that's because this is a more complete expression than this one. Again, it's just the energy associated with pulling charges in. This is the energy associated with pulling charges in, and also with the fabrication of those charges as well. We talked a lot about the superposition principle, saying that force obeys it, fields, potentials. Work does not obey the superposition principle. That's one big difference before. And as such, there are always just a limited number of cases where you can calculate the work. So basically, if you're any textbook, you're going to be seeing an example like the one I worked, or with asking you to calculate charge distribution, uniform charge distribution. You might be asked to calculate the energy associated with a charged shell with a certain radius with a uniformly charged shell. So as I said, limited number of problems that you can do here. But anyway, this is how to calculate work, and just be mindful of what these two mean. Now, this also begs another question: where is the energy stored? In one case, we seem to be saying, well, it's associated with the field. In the first case, we seem to be saying, well, it's stored with charges. There are instances in mechanics, too, where you say, well, what's your point of view? Where is it stored? Yeah, to give you an example, like an elastic spring. And you've got a compressed spring, you've got a mass, and then you release it, mass travels away, and kinetic energy increases. So where's the energy stored there? Is it stored in the region of space? Is it stored in the spring itself? So as far as we're concerned here, it really doesn't make any difference in electrostatics where you say that energy is stored. If it's stored in the charges or it's stored in the field. When you move on to a topic like general relativity, as it turns out, it is more useful, I should say, beyond useful, it's essential to assume that is associated with the electric field. This concludes the lecture on work and energy. Next time around, I will be discussing boundary conditions, and we'll start talking about Laplace's equation in a great deal of detail, and we'll look at the couple of techniques for solving that. One's method of images, and the other is separation of variables.